Hi, kiddos. This is for Module 21.3, Combinations and Probability. The essential question is, what is the difference between a permutation and a combination? So, permutation, we've already learned that there are several different ways we can order um, our selections from our certain trials in probability. But now, what is combination? So, our shortest answer is that you can choose a number of objects in such a way that the order matters. Okay, in which case you choose a permutation. So again, permutation, order matters. Okay. Now, or you can choose in such a way that order does not matter. So keyword is does not matter, which in case you choose a combination. So permutation matters for the order, but order does not matter for combinations. So again, the definition, a combination is a selection of objects from a group in which order is unimportant. So order is not important. For example, if three letters are chosen from a different group of A, B, C, and D, well, there are four different combinations. So again, we're only selecting three letters. You could try ABC, ABD, ACB, BCD. But again, order does not matter. All right, so example one, a restaurant has 8 different appetizers on the menu as shown in the table. So hopefully you're already thinking, well, okay, 8 factorial, probably you're probably thinking something like that. That's healthy. Okay. So they also offer an appetizer sampler, which contains 3 of the appetizers served on a single plate. So you've probably already thought, like, well, we have 8, but we're only having 3 permutations. If you're thinking that, that is good. All right. That means you were on target for your thought process. So this is on a single plate. Now, how many different appetizer samplers can be created? The order in which the appetizers are selected does not matter. Aha. So instead of a permutation, we're thinking combinations. But first, let's approach this as if we were doing permutations. So first things first, again, we have 8, but we're only picking 3. Um, well, hopefully you thought this, right? 8 factorial, because again, we have 8 appetizers. All right. And then we have, again, the number of choices minus the 3 that you are selecting. And you should get 8 factorial over 5 factorial. Now, just to kind of refresh your memory on how to deal with factorials, 8 factorial is really 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 5 factorial is really just 5 times 4 times 3 times 2 times 1. And if you really notice, well, these 5 cancel out, these 4 cancels out, these 3's cancel out, these 2's cancel out, these 1's cancel out. All that's left is really just 5 times 7 times 6, which should give you 336. So remember how to deal with factorials. This will come up later in your career, and it's something to kind of keep in the long-term memory. All right, so again, so this basically says, well, there's 336 different permutations that you can pick, certain 3. That's a lot. All right, so now we're going to find the number of different ways to select a particular group of appetizers. This number of permutation is of 3 objects. So you have 3 objects, but now it's like, all right, we're going to talk about the order and different ways we can get those 3 things moved around. So again, there's 336 possible appetizers. You can get nachos, potato skins, beef chili, or you get chicken quesadilla, nachos, potato skins, or you can get, quesadilla, egg rolls, soft pretzels. There's 336 different permutations in which you can choose 3 appetizers, and that was part A. Okay, but now, well, what order do you want them to come in as? Okay, so what's going to come first? Well, you have 3 objects, right? 3 appetizers, and you're got 3 of them, and you're choosing 3 in a certain order. And that's just going to be 3 factorial over 0 factorial, right? Because 3 minus 3 factorial gives us 0 factorial. And again, that should just be 6 because 3 factorial fun fact, is just 1, and 3 factorial is really just 3 times 2 times 1, which is just 6. So that's how they got 6. So there's 6 different ways you can get it. For example, if you got nachos, quesadilla, and potato skins, you could do nachos, then quesadillas, then potato skins, or you could do quesadilla, nachos, then potato skins, or you could do potato skins, quesadilla, nachos. There's 6 different ways you can really get those to come out for your order. All right, so let's see. Part C. Find the number of different ways to select a particular group of appetizers. So this is the number of permutations of 3 objects. Oh, wait, no, that's B. All right. To find the number of possible appetizer samplers in order of selection does not matter. Okay. So now we're kind of getting into the new material here. So order does not matter. Well, we had 336 options, right? And no matter which option we pick, we're still going to have 6 different combinations for those 3 orders. So we're going to have 6 different ways of handling that. So 336 divided by 6, and there's 56 different combinations. Interesting. All right, so this is the beginning of. Okay, so basically, what we did here for part C was we had 8 picking 3 divided by 3 picking 3 to get part C. Okay, so note that, and we're going to cover it and explain a little bit further. All right, so finding a probability using combinations. So you probably, again, we took 8 pick 3, right, divided by 3 pick 3. Now, that was because order does not matter. So this rule is what we came up from with these appetizers. Combinations. So this is the main thing. The number of combinations of n objects is taken r at a time is given by this. So please remember that. Looks familiar, right? Because if you remember in PR, it was just n factorial divided by n minus r factorial. But the difference now is for combinations, we have r factorial because order doesn't matter, and that changes some things. Okay, it's like order mattered when somebody got elected president, and the other what 7 people were thinking, oh, maybe I'll get president, But in this case, combinations doesn't, have that situation. Nobody's going, "Oh, I didn't win president. Gee, I might get vice president then, hopefully." There's none of that. It's like somebody gets picked for something, and the other 7 people are like, "There's still a chance. There's still something going on." Okay, so combinations doesn't matter about order. All right, so let's go ahead and use this, and we'll show you some more examples. All right, so example 2, find the probability. So there are 4 boys, okay, 8 girls on the debate team. The coach randomly chooses, 3 students to participate in the competition. What is the probability that coach chooses all girls? Okay, so that is the main question. What is the probability that the coach chooses all girls? All right, so our sample space consists of combinations of 3 students, okay, because he could pick, a boy, a girl, a boy, but in reality, he has to pick all girls. So we have to figure that out eventually. But there are a total of 12 students, right? There's 4 boys, 8 girls. That's 12 kids. All right. So hopefully you're already thinking, well, we got 12 kids. We have uh, 3 selections. And then again, for uh, this 9 factorial, where did it come from? Again, they had 12 choosing 3. And if you rewrote that, that's just going to be 12 factorial all over 3 factorial, right? We're choosing 3 different combinations times 12 minus 3 factorial. There we go. All right, and that's where we got the 9 factorial, by the way. Okay, so if you're confused on where that came from, it came from the formula. All right, so there's actually 220 different ways of this coach selecting his kids. All right. Now, event A consists of combinations of 3 girls taken from a set of 8 girls. Okay, so now we're talking about, so here's all the different ways of, him picking boy, girl, or boy, or something like that from those 12 kids. So again, that could be like Sally, Bobby, Kenny, Sally, Frank. There's just so many different ways this coach can pick people. But now we're talking about event A, where it's like, well, only the girls get picked. So for that event, it's really, well, the number for that event is going to be 8 choose 3. So 8 choose 3 is this 8 factorial divided by, again, we're choosing 3, and then 8 minus the 5 that are left over. Oops, not 5, the 3. Sorry, my brain is rushing. Minus 3. There we go. And we get 8 factorial all over 3 factorial times 5 factorial. Okay, so we got 56. Now, to figure out the probability of that, we just take the number of elements in set A, or event A, and divide it by the sample set. All right, so here we actually just take 8 choose 3, because that'll be for all the girls, and divided by the entire sample set, which is 12 choose 3. And that'll give us our answer, which is 14 out of 55 chance that we're going to get nothing but girls. All right, it doesn't matter which girls get picked. It could be Sally, Betsy, and Tiffany. It could be Tiffany, Sally, and Betsy. It doesn't really matter, but there's a 14 out of 15 or 55 chance that that's going to happen. So please note this idea. Okay, that's choosing 3 girls, right? And there's 8 total, right? So there's 8 girls total, but you're only picking 3. And then this is the entire sample set, so total students. And again, the coach is still just picking 3. All right, so all girls. There we go. All right, so that's the idea of combinations. All right, so example 3, find each probability. So there are 52 cards. Ooh, I love cards. All right, so 52 cards in a standard deck. 13 in each are 4 suits. So that's clubs, diamonds, hearts, and spades. All right. 5 cards are randomly, okay, keyword there, keyword, key thing. 5 cards are randomly drawn from a deck. What is the probability that all 5 cards are diamonds? So let's talk about this real quick. We have 52, so our sample set, okay, sample space. We have 52 cards, and we're choosing 5, okay? So that's going to be 52 factorial. And then again, order doesn't matter here, okay? So there's 5 different, or combinations that can happen. And then what is 52 minus 5 factorial? And you should get 52 factorial divided by 5 factorial and times the 47 factorial, because 52 minus 5 gave us that 47 from here, okay? Now, your calculator can do a lot of the legwork here. You could also realize that in reality, this is really just 5. Oops, thank you, computer. So again, if you know your factorials, you know that really what you're doing here is just 55 or 52 times 51 times 50 times 49 times 48 all over 5 times 4 times 3 times 2 times 1. Now, I know what you're thinking, Mr. Webb, what happened to the 47, times the 47, 46? Well, they got crossed out by the 47 factorial, so they really just canceled each other out below that point. All right, so if you do this correctly, you should realize that there is, yeah, 2,500,000. So go ahead and practice with your calculator totally. Also be aware the math button on most calculators can get you to probability, You spell it out with PRB, and there should be a and choose R button there. So you get some number, you go to math, probability, NCR, and then once you press that, and then you just plug in the next number, it gives you your answer. So it could do this for you. All right, so you get 2,598,960 different ways we can really pull out these cards. That's a lot. No wonder we use this for games, right? Now, event A. All right, so what is the probability all 5 cards are diamonds? So we're talking about a flush, right? So that's a specific hand that is a pretty strong hand. I mean, it's something, something is better than nothing. Now, 5 cards. So event A, all 5 are diamonds. Well, each suit is 13 cards, so that means we have 13 diamonds that can exist total. So, what is the odds of those 13 cards of where we draw 5 of them? So, well, there's 13 diamonds, right? And we're picking 5. And what's 13 minus 5? 8. And that's how we get that. Now there's 120, or I'm sorry, 1,287 different combinations in which we get nothing but diamonds, um, or the way we can draw diamonds. But again, the probability of selecting those 5 cards for diamonds is basically just this. We have the event A, where we draw the diamonds, divided by the total sample space. So we just take these two numbers. So we take 1287 and we divide it by the 2,598,960. Once you do that, the book, they always like to mention that you could reduce, which is healthy. Um, if you actually do this in the calculator, you're going to get 0 point something, and you're going to realize that's just a really small percentage. So it's really rare to get a flush like that. I mean, if it happens, it's like equivalent to seeing a lightning strike hit a tree right in front of you. It's kind of cool. All right, moving on. Your turn number 1. A coin is tossed 4 times. What is the probability of getting exactly 3 heads? All right, so tossed 4 times. What is the probability of getting? So again, think about what's my event, divided by my sample set. So you should probably think about how many different ways this can work. Now, a coin has how many sides, right? You should probably think about that. So if you think about sample set, okay, there's 2 different ways, right, of getting something times 2 different ways times 2 different ways times 2 different ways. You're flipping this coin 4 times, and there's going to be 2 different results that could happen, right? So your sample set is really 16. You have 16 different possible outcomes, but you're basically just choosing that, well, in those 4 times that you roll the dice, or I'm sorry, you flip the coin, that you're choosing exactly 3 heads. So that's as much as I want to give you. But yeah, know this probability of that event occurring will be that. But again, I'm not going to give you the whole thing. I kind of want to see you and see how you operate there. A standard deck, so this one right here, of cards is divided in half. That's important to know. That's going to change a lot. So instead of using 52 cards, you're going to divide by 2. You're going to have 26 cards. So that would probably be your sample space to work with. But again, how many are we drawing? Yeah, we're drawing 4 cards from the red half. Okay. Um, so you should be thinking 26, choosing 4. Okay. And whatever that gives you. And then next thing you know, and that's again for your sample set. Okay. Now for your event A, what is event A? That we're choosing 4 cards, and then what is the probability of getting all diamonds? Okay, so all diamonds, so we're talking about a suit, right? We're talking about a certain And we all know that suits come in 13s. And what if you're choosing all four that happen to be that? And then just remember probability, same thing down here. And that should probably take care of you there. All right, moving on. So, finding a probability using combinations and addition. So, sometimes counting problems involving the phrase at least or at most. Um, most of the time, you see something like greater than 11, less than 4. But what about at least and at most? So, the previous chapters didn't really do that, but now they're kind of bringing this up. When they say at least or at most, combinations must be added. You must be using combinations. All right. So just be aware of the wording sometimes. In college, especially, words matter in the problems. Okay. So, for example, suppose you flip a coin 3 times. Okay. The coin could show heads 0 times, 1 time, 2 times, or 3 times. Who knows, right? But that's the possible scenario that could happen. Now, to find the number of combinations with at least 2 heads, all right, we're going to add the number of combinations with 2 heads and the number of combinations with 3 heads, just how it says there. Okay, so um, we know that hey, we're flipping the coin 3 times. All right, so that's the 3 flips. We know that if we flip and get 2 heads, then we have to add that to the idea that we could flip 3 coins and still get a third head for our outcome for our event. So that's something to consider. All right. Same thing if you were to get 1 coin. Oh, that means you can still get, um, 2. You could still get 3. Really depends on the scenario. So let's look at some examples and see what's going on there. All right, so example 4, a coin is flipped 5 times. What is the probability that the result is heads at least 4 of the 5 times? So again, this word pops up and you should already be thinking, boom. All right, you should probably be thinking that. 4 of the 5 times. So you're flipping 5 times. So hopefully, if you can remember the hint from my do now or my your turn, our sample set, again, we're flipping 5 times. There's a total of 2 outcomes each flip. That's really just 2 to the 5 power. So there's actually a sample space of 32. Okay, so there's 32 different outcomes that can really happen. Now, if we let A be the event of the coin shows up heads at least 4 times, okay, so that's here. Basically, what it's saying is the sum of the 2 events, the coin showing heads 4 times and the coin showing heads 5 times, is basically written like this. Okay, so we find the sum of the combinations of 4 heads from 5 coins and with 5 heads from 5 coins because it's still possible that we can get a fifth coin on the fifth flip. So that's something to acknowledge. It's like, hey, I got it 4 times, but what if you get it for the fifth time? All right, you also have to probably factor that in. So again, just like how we showed you, that's just 5 choose 4. This is 5 choose 5. If you do this correctly, you get 5 plus 1. That's 6. Now, if we talk about probability, again, if you notice, probability is still just going to be the event divided by your sample space. So the event could happen 6 different times out of 32, and we could reduce. So there's a 3 out of 16 chance that we can get heads on our coin flips. So 3 out of 16 for that. And again, we had to add in the fact that it's at least. Okay, so yeah, you can get 4, but what about if you get a fifth head flip? Because technically you're still getting at least 4. So that's why we have to add in the idea that we can get the fifth. Okay, that's why we had to do that. All right, so let's look at example 5. 3 number cubes, or yeah, cubes, number cubes are rolled. As a result, is recorded. What is the probability at least 2 of the number of cubes show 6? So the number of outcomes in the sample space S can be found by using the fundamental counting principle, since each roll can result in a 1, 2, 3, 4, 5, 6. Okay, so there's a total of 6 different options, and we have 3 dice. So, what is the probability of at least getting um, 2 of them to show up 6? Well, we have 6 different numbers, but we have 3 different dice. Isn't that just 6 to the third power, right? Because we have really just 6 times 6 times 6, right? So that's just going to give us 216 for a sample set. And now we have to talk about the event of where we get at least 2 number of the cubes to get 6. So keyword also is at least. That means what if you get 6, you know, on 2 dice, but all of a sudden you get the third dice to also roll a 6. I think Yahtzee, right? There's 6 dice, and if they all land on 6, you scream Yahtzee, right? So it's like half of a game of Yahtzee. So 2 dice, all right, 2 cubes show 6, or 3 cubes show 6. Now, the event of getting a 6 on 2 number of cubes occurs at least. Let's think about this. Hmm. Let me think. Yeah, 5 times. Since there are 5 possibilities for another cube. Hmm. So let's see. Was it probably at least 2 of the number cubes show 6? Uh-huh. 5 times. Since there are 5 possibilities for the number of cubes. So there's 5 times that you can get 3 of your dice to at least get 2. Okay? But again, you have to consider the fact that, well, you can get the third dice to also give you 6. So in reality, that's 5 times 3 factorial divided by 2 factorial. And 3 minus 2 is 1, so it's just 1 factorial. Plus the idea that you get 3 factorial divided by 3 factorial. 3 minus 3 is 0 factorial, okay? Which should equal 15 different ways there, plus that one situation that can occur, which gives you 16. If we talk about the probability, event A, again, there's 16 different ways that we can roll a dice and still get that, but that's out of 216 rolls that you can roll. They see me rolling. All right, and we can reduce 2 out of 27, and that'll be your answer. So basically, it's like this: it's a 2 out of 27 shot of at least rolling uh, 2 sixes. But I mean, we're also including the third 6. Why not? I mean, that's technically a 6. You still get at least 2 of your cubes to show you 6. So what I want you guys to do, and this is a pretty intense thought process here, but I want you guys to discuss why it's 5 times. Okay, why are there 5 possibilities for another cube? Why? Um, why are there 5 possibilities for the other cube? Is it because if it's not a 6, would it be 5 other options? Do we have to factor that into account? And do we have to factor that into account for these 2 dice? Is that why? So I want you guys to talk to each other about that. That's a very, mind stretching one. Even I was just kind of like, wait, let me think real quick. Ooh, 5? So again, it's one of those things where talk about it, okay? Try to figure out why that 5 had to come in there. Why do we have to take care of that? All right. So Here's your turn number two. Math department has a large database for true or false questions, half of which are true and half are false, that are used to create future exams. A new test is created by randomly selecting 6 questions from the database, where the probability the new test contains at most 2 questions where the correct answer is true. So what you should probably think about is, again, what is my sample space? And what about the event? Okay. Um, you are selecting 6. So you should probably be thinking, okay, 6 choose at most 2, right? That occur to be true. What is the probability that new test contains at most 2 questions? So again, talk about it, think about it, and definitely try your best on that one. All right, so there's your homework. If you have any questions, let me know, and work together. Definitely, this is higher order thinking. Definitely, and Terry Crews make my day feel a little bit better. Hi, Terry. He gets it.